So by the end of class today, we should be able to calculate these things called fundamental frequencies. You may have heard of this if you remember from the guitar string example, right? Where the fundamental frequency on a string, right? Let's say you have a little guitar string, right? If you pluck it, this is the fundamental wavelength, and this gives you a particular frequency called F1, okay? And that produces a particular sound, but if you're able to pluck your guitar string so that it fits a entire wavelength into it, this gives you the wavelength here, right? It's lambda2, and this gives you a different wavelength, different frequency, right? And we're going to do the same thing, but now instead of, wave on the string, we're going to do that with sound waves instead, right? So remember that sound is a wave, wave on the string is a wave. All these waves obey the same, well, let's not say same, similar equations with the same principle, okay? And just as wave on the string, sound wave is probably best demonstrated this way, because as opposed to just a wave on a string, right? Sound wave emanates upward radially, okay? And the idea here is that we're going to show you is that you can have the same interference effect. I'm going to do the interference lab here. Click, right? Where if you have one wave, let's say this, right? Even though this is like a drop on water, but the sound wave, you can imagine it propagating outward like this, okay? So you got a spherical wave going outward. So just as I speak to you, right, there are sound wave that's going out, emanating from me, right, in all directions, okay? That's causing, the little eardrum in your ear to move, and then your cochlea actually detect that sound with the little hair follicle we talked about yesterday, right? But if we have two different waves that's being produced, okay, these two waves are going to start interfering with each other, okay? At some points, right, the bright part shows high amplitude, right? The dark part shows low amplitude. You can see that it creates a different pattern where you have this high amplitude blob going out this way, right? But then along this direction, right, you always have kind of a low amplitude area. And this is because of interference of waves on top of each other, right? Remember interference, right? Another word for it is also superposition, right? And that's because, let's say you want to try calculate the resultance wave, right? It's actually the summation of these two waves added together, right? Okay. And this gets complicated because this depends on x and time. This depends on x and time. So therefore, the resulting function also depends on x and time. Okay. That's for wave on a string, right? But for sound wave, right, we're going to be dealing with delta P, right? This is the change in pressure, right? As a function of actually the vector r and time. So this is like it could be a 3D thing, okay? Right? Then what happened is that this is the summation of the initial wave, right? One of the waves, okay? And then you add the change in pressure to the second wave to it, okay? And this gets a little complicated in 3 dimensions, so we're just gonna show you guys in 2 dimension, okay? Down here, right? We kind of have like a still picture representation of that previous simulation, right? Where this is a speaker that's creating sound. This is another speaker that's creating a sound around it, okay? And both of these speakers are, let's say, generating the same frequency of sound. It's making the same noise, okay? So what happened is that these little lines here represents the crest of the wave, okay? The halfway between points represent the trough of the wave, where the wave is the lowest point. Okay, so it's a little bit hard to imagine, but okay. But you can see that sometimes the crest of this speaker's wave lines up with the crest of the second speaker's wave, right? So remember when the crests line up with each other, you get constructive interference, right? when the crests line up with the troughs, that's when you have destructive interference, right? So these blue points here shows you where the blue lines, which are the crests from both waves, line up with each other. And therefore, you get constructive interference at these blue points, okay? Where you get destructive interference are these black points, okay? Reason is the black points, not the red, is because this is the crest from speaker 1, but this is giving you the trough from speaker 2, right? Remember this white part of the drawing represents the trough, right? And therefore, you have a peak overlapping with the trough, and therefore the two waves actually add to 0. Okay. The red point, the red point is when both troughs line up with each other. So you just get a double dip kind of wave, okay? So, and the idea is that, well, we can actually try to calculate where this happened if we just pick some random point P, right, out away from the speaker. So this is the moving the speaker over here, moving the speaker here, and just removing those wave drawings, right? Right. So if we just pick some point P here, right, this point P is some vector R1 away from the speaker 1. So let's call this speaker 1, right? And then is R2 away from speaker number 2, okay? Therefore, the difference in distance between the two speaker, right, it's just the magnitude of R2 minus R1, right? That's just us trying to figure out what's the difference that the difference in distance that the wave had to travel, okay? And remember, if the difference in distance between them is some multiplication of the wavelength of the sound, okay, you get constructive interference, right? Okay, so this you get constructive. Okay. But if they are half a wavelength apart, meaning one is going to a trough, one is going to a peak, the other one's going to a trough, therefore they're actually half a wavelength out of phase with each other, then you get complete destructive interference. Okay. Right? And therefore, right, you get constructive if this change in distance, meaning the difference in distance that the wave travel, is some integer multiples of the wavelength, where this integer goes from 0, 1, 2, 3. Okay, very similar analysis as we did with the guitar string, right? The wave is destructive if the difference in distance that the wave travel, right, is half a wavelength apart, okay, which is this example up here, right? This goes with this guy, right? This goes with this guy up here, okay, right? With the integer counting, you have to be more careful. It's only the odd numbers, right? Because, right, if you put 2 here, right, 2 will actually be 2 over 2, which actually is 1 times the wavelength, which is actually the place where you get constructive interference, right? So you have to be careful with the destructive. Is always the odd integers, okay? Right. As I noted even before this, right, this is basically how noise canceling headphones work, where you have a headphone that actually has a microphone attached to it near where your ear is. It also has its own speaker, okay? What happened is that you have some incoming noise, which is this red wave, okay, that you want to block out. This is the stuff you want to get rid of, okay? What it does is that this microphone will actually measure this and play it back to you, play the exact same sound, but 1/2 of a wavelength different from the incoming wave. Therefore, when the peaks lines up with the trough, right, the peak lines up with the trough, the end result is actually a wave that has no amplitude, right? And therefore, you can actually cancel out noise by adding a different noise to it, which is kind of weird, right? You play through 2 different sounds and you get nothing, right? Okay. 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 So sound is also produced not just from guitar strings and noise canceling headphones, right? Like for example, we ourselves make noise. as we demonstrate here a lot, right? So the human, let's say the human instrument, right, is actually made up of basically our trachea with this thing called vocal cord. There's actually a picture of it up here. Okay. This vocal cord is really a little muscle that kind of opens and closes and allows you to basically change, right, the diameter of the sound that's the diameter of the opening in your trachea, okay? Right? This in combination of your tongue can change the shape of basically your trachea plus your mouth. And this allows you to actually create different pitches of sound. So if I want to make a high, sorry, high pitch sound, right? I have to like kind of use the muscle in the back of my throat. If I want a low sound, right? I'm using the muscle in the back of my throat basically to change the shape of the back of my mouth in order to make that sound, okay? This is actually a open tube, okay? If we model it in a physics simple version. But of course, the human mouth is much more complicated than just a tube, but we actually will see how certain musical instruments that are fairly simple, we can actually model them as these simple tubes and actually be able to figure out what type of wavelength or frequency of sound they would produce, okay? And the way we do this is by following the same example we did in chapter 16 with the guitar string, right? Remember when you pluck a guitar string, right? Both ends of the guitar strings are fixed. This creates a boundary condition. That means the guitar string cannot move at the ends, right? When you pluck a guitar string, it can either vibrate with this wavelength, okay? This wavelength is actually 2 times the length of the guitar string, right? Because to complete the wave, you actually have to extend this out, right? So this is actually lambda over 2. This is lambda over 2, right? Therefore, the length of the guitar string, okay, is actually 1/2 the wavelength if you just pluck it once, but you can pluck it so that it oscillates with basically 1 full wavelength inside, right? Or 3/2 wavelengths inside, or 4/2 wavelength inside, right? So these are the different frequencies of sound a guitar string can make, okay? So we can do a similar analysis with tubes, okay, that makes sound. So one type of tube that makes sound is a clarinet. Anyone ever seen it play a clarinet? I think no one from the music department here. Okay, a clarinet is actually a closed at one end, open on the other end system. Okay, so the clarinet has this thing called reed. You actually physically do not blow air straight into the clarinet. What you're doing is you're blowing on this reed, which is actually just a little piece of plastic that vibrates. And that actually causes vibration here. These vibration then moves the air in your clarinet tube in order to produce sound. Okay, so the physics model of this is that you just take the end of the clarinet and model it as a tube where one end is closed, the other end is open. Does that make sense? Okay. And if you've ever seen a clarinet, may not be. Okay. So the idea of a clarinet is that the air that you blow actually never, you can't spit on people with a clarinet. Where we're going to see you can spit on people with a flute if you want. Okay. Okay. So what happened is that this creates, just like the guitar string, some sort of boundary condition where, right, at the closed end, right, the wave cannot go up and down, right? Therefore, it's fixed to have 0 amplitude here. Sorry, 0 displacement here, right? But at the open end, okay, it has to fit into this tube. Therefore, it has to have its maximum amplitude out at the open end, okay? So this is, right, delta P here has to be 0, where delta P here has to be basically delta P max. I would actually prefer to call it amplitude, but The book uses the notation of delta P max as amplitude, right, for sound waves. Okay. So this sets up a bunch of interesting conditions where, well, if I have a wave that's like this is actually, let me draw this again, right? This is actually the peak of the wave. If I go back down to 0, right, that's half the wavelength. So this gets to wavelength over 2. And then if I complete the wave, then I get the full wavelength, right? So what actually fits in the tube is actually 1/4 of the wavelength. That makes sense? So therefore, the conditions that a clarinet / an open closed tube system, okay, is enforcing that the wavelength that fits into that tube is 1/4 of the wavelength. Okay. Of course, that's not the only wavelength of sound that will fit in there. There are higher frequencies of sound / lower wavelengths of sound that can fit into this closed open tube system, where you can have 3/4 of a wavelength. Okay, so this is where it fits. Okay, or you can have, I think this one is 5/4 of a wavelength. Sorry, I cut off the 5 up here. Okay, or 7/4 of the length. Okay, and you can see that this is the longest wavelength. This is the second longest wavelength, the third longest wavelength, the fourth longest wavelength, right? So as you increase the number of wavelengths you fit into the tube, you're decreasing the wavelength of the sound that you're making. When you decrease the wavelength of the sound, what happens to the frequency of the sound? If the speed of sound is constant, it gets higher, right? If you so remember that speed of sound, right, is always wavelength times frequency. If wavelength goes down, right, the frequency has to go up if the speed of sound is the same, right? If you're not changing the speed of sound, okay? So these are equations that will be given to you in the test, but we have to learn how to use them. So this is the condition where, well, the wavelengths of the sound that fits into my tube is going to be 4 divided by n, where n is one that's, again, odd integers, 1, 3, 5, 7, 9, 11, blah, blah, right? Okay. The reason we cannot use the even ones, if you do the even ones, you actually end up with the other side. Okay. But, right. So the wavelength of sound that will fit in your tube is 4 times the length. The 4 comes from the fact that the fundamental wavelength is 1/4 the length of the tube. Okay, that's where this 4 comes from. Okay, all the other ones are just going to be odd integers. Okay, using the fact that, well, if you want to convert, right, wavelengths to frequency, right, you can always convert between the two, right, because the frequency is just going to be V over lambda, right? You plug that in there, what happens is that you convert this not to calculate the wavelength of the sound that will fit in your tube, but the frequencies of the sound, right? So notice that as n increases, right, the wavelength decreases, just as we said. But since frequency is inversely proportional to the wavelengths, right, as we increase n here, the frequencies go up, okay? So the higher and higher overtones, these are called overtones. This is the fundamental frequency. This is the first overtone. This is the second overtone. We don't have to know that for the test or anything like that, but it's just a musical term. Okay. The higher overtones are actually higher and higher frequencies. Okay. And typically what you will hear most of the time, okay, when someone plays the clarinet, is you hear mostly the fundamental frequency, and then you hear a little, like a little bit of the first overtone, much less of the second overtone, and much less on the third. Okay. Okay. So when someone plays a musical instrument, it's actually combinations of the fundamental frequency plus all the overtones superimposed on each other. That's what's causing the sound to be made in your ear. Okay. Right, any questions about this? So this is actually I think the rest of the lecture is not going to be equation-y at all, right? But I'll do an example. just to show you guys how to do the stuff in the worksheet. Any questions before I do the example? Okay. All right. So this is not a musical instrument. What we're going to do is actually use a tube of water to measure the temperature of the air. Okay, let's see how this can work. Okay, so we have a physics student like yourself. Okay, and we found that there's an air column tube. Okay, closed at one end. Okay, but then open on the other end. So the first thing we want to start doing is actually start drawing the system. Okay, you can imagine this as like maybe like a graduated cylinder that someone just put in the chemistry lab or whatever. Okay, what happened is that they hold the tube constant while initially the tube was filled with water. Okay, let's say filled with some water. Okay, and they basically lowered the level of the water. Okay, until it resonated with a tuning fork that has a frequency of 256 hertz. Okay, and the student found that while the first resonance, meaning the fundamental frequencies, occur when she dropped the liquid level from the top to be 0.336 meters. Okay, so in this case, right, since we're dealing with the first resonance, okay, that's actually F1, okay, and therefore that's equal to 256 hertz. Okay, the length of the tube, okay, at that first resonance happens to be at 0.336. And the question is asking you for what is the temperature? Okay, how do we figure this out? Anyone have an idea? How is temperature related to the frequencies of sound or the wavelength of sound? Through the speed, yeah. So this was from a couple of days ago, right? The speed of sound, okay, in air, right? We can calculate it using like the more complicated Boltzmann constant one. But the one I usually remember is that, well, I know the speed of sound in air at 0 degrees Celsius, okay? Okay, and I just have to multiply that by the temperature in Kelvin divided by the temperature of 0 degrees Celsius in Kelvin. And that with a square root allows me to convert to any speed at any temperature we want, right? Okay. So as usual, right, the speed of sound is always, well, speed of any wave is always the frequency times the wavelength. Oops, frequency times. Yeah, let's not do that. Let's go back up here and just get to the equation we need, right? So here, right, we have an equation that allows us to calculate the frequency of the first fundamental frequency, F1. Okay, let's just write down the general equation. Okay, let's just go back up. Okay, there's a 4 up down there. 4 times L, right? Where L is this L that was given to us. N, right? N is equal to 1, right? Okay, and the speed of sound can be calculated using this equation I just wrote on the top here. Okay, therefore, F1, right, is going to be 1 times the speed of sound. Instead of writing the speed of sound, I'm going to write 331 square root of TK over 273, right? That's the speed of sound, divided by 4 times the length of the tube that was just made, right? The length of the tube we just made because the water makes a closed end, right? That's basically, it allows us to change the length of the tube dynamically like this, right? The length of the tube is 0.336. And all of this is in meters, okay? This is in meters per second, so we're good, okay? Right? And this tells us that the frequency is 256 hertz, okay? So we need to actually solve this equation for TK. If we solve this equation for TK, then, it's gonna be, I'm gonna do it in 2 steps actually, because there's too many algebra steps, okay? I'm gonna multiply this side by 256 times 4 times 0.336 m, and then divided by 331. You guys kind of see what I did. I think I moved like 3 things in the algebra step, right? I moved this up here, move this up here, and move this down on the bottom, right? Okay. Then you square both sides, okay? Then you get TK equal to this whole thing squared, whatever this is, right? Multiplied by 273 Kelvin. Okay, let's see what that number is. Okay, 256 times 4 times 0.336 divided by 331. The whole thing squared times 273. And I got the temperature in Kelvin to be 293 Kelvin. Okay. Okay. Is 293 Kelvin sensible for maybe a around room temperature? Maybe people are not familiar with Kelvin scale, right? I can convert this to Celsius scale, right, by just subtracting 273 from it. This is actually 22 degrees Celsius, right? And that's around what room temperature is. And unfortunately, we're not going to convert things to Kelvin. If you want, you can do that to see if it makes sense to be room temperature. I think that's about 75 degrees Fahrenheit, okay? Okay, any questions about this? All right. So that's what we're going to play around with on the worksheet. But before we jump to the worksheet, I want to just kind of go over the next, the other type of tube, which is actually what actually you need on the worksheet. We actually have we're going to do a flute in the worksheet. Okay. Okay. So there's another instrument called a flute. Instead of having just a single open end like the clarinet, the flute actually has 2 open ends. Okay. Where you actually blow in from the side and then the air actually come out on both sides, okay? In this case, right, you have an open tube, okay? That's what these are called, okay? So in this case, right, the boundary conditions of the sound waves is that they both have to have its maximum amplitude on both ends, okay? In order for that to happen, right, the middle of the tube actually have to have its to be 0, okay? Because that's the only way I can draw a sine wave in here, right? Okay. So in this case, instead of only 1/4 of a wavelength fitting here, right, it's actually always a half a wavelength that fits in here. I see that? Because if I extend this out, this is half a wavelength, right? This, and that completes the wave. Okay. I can even do it to the left here, right? Okay. Let me just draw the tube once again. Right? This tube has some length L. Okay. The wave I'm able to fit in here, right, is this shape. Okay. But that's not the full wave, right? In order for it to be a full wave, you have to come back to the same point. And therefore, right, this is actually wavelength over 2. This is wavelength over 2. And that gives you the full wavelength, right? So the wavelength that fits in the tube length, right, is actually only half a wavelength. Does that geometrically make sense? Or is that confusing? Okay. Right. There are higher frequency, shorter wavelengths you can fit in the tube. The boundary condition you have to enforce is that it has to have its peak amplitude, right, at the ends, right? It has to have this, have to have this, have to have this, right? And then so you can fit more waves in here, okay? The ways you calculate the wavelengths that will fit into a tube with a particular length L, right? It's going to be 2 divided by n, where n, once again, is 1, 2, 3, 4. So sometimes be a little careful. This one is all the integer, not the only odd ones. Okay? So, and then if you want to calculate this in wavelength, right? Once again, you use the relationship that speed of sound is just the frequency times the wavelength. And that allows you to calculate it to convert that equation to the frequencies of sound that a flute, in other words, an open tube system would produce, okay? And that's actually what's going to be on the worksheet today. Okay. So probably want to copy these guys down. And this one you should always know, okay? The speed of sound is the frequency times the wavelength, okay? Okay. With that, I just kind of, with section 17.4, We're not going to do any like problems on it. I just want to show you guys how different musical instruments actually work, right? So when you pluck a string on the guitar, or throw the pen on the floor, you pluck a string on the guitar, the sound you're actually hearing is actually not directly coming from the guitar string, okay? It's actually coming mostly from the body of the guitar, okay? This body acts as kind of like a resonator for the vibration from the guitar string, okay? So the guitar string is going to vibrate up and out. That's going to produce sound wave that's going out from it. But most of it, well, half of it will be caught by the body of the guitar itself. And the sound actually resonates in there and it builds up to make it louder and louder and louder, okay? Remember when you have a resonance, right? It's like the same idea as if you were pushing someone on a swing, right? If you push it at the right frequency, that person will swing higher and higher and higher, right? If you do not, right, then you're doing some random pushing. What happens is that the amplitude of that oscillation doesn't get bigger. Same thing with waves, right? Because waves and oscillations, wave on a string, all of this obey the same set of equation, okay? So this guitar actually acts as a resonator to basically amplify the sound that's produced by the guitar string when you pluck it, okay? Similarly, if you have a drum, okay, drums of, well, this is, I'm not sure what these drums are called, but drums of different sizes, because I think the interesting thing is that you have a drum that has a very small size, bigger and bigger and bigger size, right? These bigger and bigger drum means longer wavelengths of sound will fit in there, right? And remember, longer the wavelength, the lower the frequency, right? That's why if you actually have some object that you're banging on, right? The bigger that volume, the lower pitch the sound is going to get, okay? So this is how you can actually produce different sounds with drums, okay? And for this vibration to be, let's say, for the resonator to work very well, you actually want the material to be very rigid. For example, if you're making a violin, you don't want to lose a lot of the sound just because of the vibration of the material that that violin is made of. And this is the reason why if you were to go out and buy wood for violin, these could cost you, up to like $1,000 for a plank of wood, because these woods are treated to be extremely dense, right, and extremely hard, so that it actually acts as a very good resonator. Okay, so that's sort of like the conceptual overview of it. There isn't actually any problems we can do on this for this class. Okay, but I just want to let you guys know that just because if you take a string, right, put it in the air, and you say, oh, I don't hear any sound from that string, and that's because you don't have a resonator around it. Okay. All right. Any questions? I'm going to stop recording and pass out the worksheet.